Welcome back to this lecture series on pulse width modulation for power electronic converters. So, we have this course going on. We have covered quite a few modules in this course. Each module, like probably the very first module on power electronic converters was a little on the longer side. Many of the other modules are probably 2 to 3 lectures or maybe 3 or 4 lectures and so on and so forth. So, we have looked at an overview of the various topologies and some applications of overview of the applications of voltage source converters, some basics of pulse width modulation. Then we looked at this generation of pulse width modulation at low switching frequency. This that one purpose is to learn about that. So, we keep the number of switching angles low, so that we start understanding how the harmonics are and how they affect the performance, etc. The other reason that why we go for low switching frequencies when the power levels are pretty high. Therefore, the inverter cannot really switch at high frequencies, because every time it turns on and turns off, every time a device turns on and turns off, there is a certain amount of switching loss, energy lost, and therefore, it cannot turn on and turn off more than a few cycles in a second. So, that is why if some many high power inverters would switch at rather low switching frequencies. So, you might just have a few hundred hertz of switching frequencies, for example, whereas at medium power levels you can look at a few kilowatts, a few kilohertz of switching frequency, and at low power converters like MOSFET converters you may even think of 100 kilohertz, etc. going there now. Incidentally, today this present module, our discussion is being actually on this evaluation of inverter loss, and is actually switching loss, and that switching energy loss is basically the reason for the high power inverters operating at low frequencies. Then after that low frequency PWM generation, we also looked at high frequency PWM generation, both through the triangle comparison approach and also through the space vector approach. And after that we have been focusing on certain analytical portions, like how do we analyze the ripple that is there in the line current when the here of course we are assuming that the switching frequency is much higher than the fundamental. Similarly, how do we analyze the DC link current, how much is the RMS current flowing through that, what is the DC component, so on and so forth, and again analysis of the ripple torque, how much ripple torque. So, these are the previous modules we covered now. So, presently we have been dealing with this evaluation of inverter loss. In the last lecture we covered the conduction loss aspect, and today we will be doing the switching loss. So, that is what we will continue today. And the future modules which remains to be done are actually the effect of the inverter dead time and its compensation. So, the non-idealities, there is a forward drop that causes conduction loss, which we dealt with in the last class, and again the other non-ideality in the actual switches is that they take finite amount of time to turn on and turn off, and there is a certain amount of switching energy lost, and that is the switching loss which we are dealing with in this present lecture. In the future modules, what we will do is, since it takes some finite amount of time, one consequence of that is the loss. The other consequence or other thing requirement is that the complementary devices, it can be switched really in a complementary fashion. That is, the moment you switch off one device, you cannot switch on the other. You will have to wait for a while before you can switch on the second device. So, that is what is called as dead time, and that has certain impact on the output voltage of the inverter, and we will be looking at that and how to compensate that in the next couple of lectures, the next module. And again we would look at over modulation, that is where we can operate not really in the linear modulation zone, but we go into a non-linear modulation zone all the way till square wave mode or 6-step mode, and then the final module will be PWM for multi-level inverter. So, now we are back to the present module. So, we looked at ideal and real switches, and we looked at the forward characteristics of certain devices. For example, MOSFET behaves more like resistance when it is on, whereas bipolar transistor has VC SAT. Its voltage, device voltage tends to be reasonably fixed, changes only moderately with current. So, it is more modeled better as a voltage source in its on state, or maybe a voltage source in combination with a resistance. So, such kind of forward characteristics, and how you would go about evaluating the conduction loss at any given modulation index with a particular PWM method, and again how would you do it for various PWM methods. These were the subjects we looked at last time. Today our focus will be on the turn on and the turn off energy loss, because the switches, these real switches take a finite amount of time to turn on and turn off, and before let us say the voltage falls down to 0, the current builds up, and therefore, there is a considerable amount of power dissipation during the turn on transition. The story is similar during turn off transition. So, we would look at that energy lost in turn on and turn off. We will try to get some idea on the energy lost, and we will try to see how we could possibly evaluate the switching loss for different PWM methods, and subsequently we would go on towards simplified evaluation of switching loss and design of PWM for reduced switching loss. Alright. So, it would be today. So, as I just mentioned before, we would look at evaluation of switching loss in 3-phase inverter, right. So, this is the 3-phase inverter. So, every leg is a pair of complementary switches. So, one turns on and turns off, the other turns on, and vice versa. But during every time there is a turn on and turn off, what happens? See, initially there is this voltage, when let us say this is conducting. So, the entire voltage is being blocked by this. So, when this device is to be turned on, then what happens? There is voltage across that, and the voltage has to collapse down to 0, and the current has to rise through this particular device. So, before the current the current starts rising well before the voltage starts falling, and therefore, there is a certain amount of loss here. So, which is what we are going to look at today. So, the loads are connected, and there will be fundamental and the harmonic components also. As you will see, with the harmonic components, their effect on the switching loss would be negligible, because the harmonic currents themselves might be negligible compared to the fundamental current when you are switching at a fairly high frequencies. And of course, switching loss is mainly a concern at high switching frequencies, and this is in the load, and this is the DC side, and the DC source is really connected there, and how much DC link current flows, etc., the capacitor current flows we had seen previously in an earlier module. So, today our focus will be on what are the kind of losses that you will have in these IGBTs and diodes. As I already mentioned to you, let us say for one direction of current, the conduction will be either this IGBT will conduct or this diode will conduct. For the other direction of current, either this IGBT or the diode will conduct. So, current will actually commute from here to here or here to here, depending on the direction of the current now, right. So, as we saw earlier, ideal switches have 0 on state drop, and how much ever current may be flowing through that, the voltage across that is 0, and therefore, the product of voltage and current is 0, and therefore, there is no power dissipation. Therefore, there is no conduction loss in an ideal switch. Also, let us say an ideal switch is in the off state, then there is supposed to be some leakage current. If the switch is ideal, the leakage current is 0. So, once again the product of voltage and current is 0, because current is 0. So, there is no off state loss. Again, the turn on and the turn off transitions are instantaneous. The moment it starts turning on, it is already on. The moment it is starting turning off, it is already off. So, they are instantaneous turn on and turn off. During turn on, the voltage is expected to fall down from whatever voltage it has been blocking down to 0, and the current is expected to rise from 0 to whatever the current it is expected to conduct. These two will happen instantaneously. Similarly, during turn off, whatever current it has been conducting will fall down to 0 in an instantaneously, and similarly the voltage across that will rise instantaneously. So, this is what happens in an ideal switch now. So, since there is no finite duration, there is the voltage falls and the current rises. So, or the current falls and the voltage rises, both are never high concurrently, and therefore, there is no energy loss during switching transitions in an ideal switch. But that is not the case in a practical switch. As we have seen before, there is a finite amount of forward drop. Hence, whatever current might be flowing through that, this forward drop multiplied by the current is the power dissipated in the transistor, and therefore, there is some conduction loss, which was our subject for discussion in the last class lecture. Then even in a practical switch, the leakage current is negligible, and whatever loss it could cause is negligible, thankfully, and we normally ignore the off state losses in most power semiconductor devices. Alright. So, how about the transitions? The turn on transition is finite, and that is probably cause for the problem now. So, turn on meaning the voltage has to fall down to 0, it will take a finite amount of time for the voltage to fall down to 0. Again, the current has to rise from 0 to the full value. Will it rise instantaneously? No, it will also take finite amount of time, and in fact, the current would rise first and then the voltage would fall, as we will see shortly, and therefore, what happens, the product of current and voltage is very high, not just significant, the product is very high. The voltage can be as high as the DC bus voltage, and the current can be as high as the current that it is conducting. So, the peak power can actually be the product of the DC bus voltage and the instantaneous load current, and that can actually be very high. It can be in kilowatts, it can be in tens of kilowatts. For example, if you are switching 600 volts at 100 amperes current, so let us say there is a particular instant of time when the device is still blocking entire 600 volts, but the current through that has risen to 100 amperes, and therefore the product of thing is 600 volts into 100 amperes. So you can see that it runs into tens of kilowatts. Alright, so there is a significant energy loss during the switching transition. So one of our things today will be to actually get some idea on how to calculate this, how to get these losses, etc. And we will have to go about evaluating the switching loss, like we did for the conduction loss in the last lecture. Today our focus will be on evaluating the switching loss. Alright, so this is something that tries to illustrate the turn on process of an IGBT. So it is blocking certain amount of voltage. This voltage, let us say, is the DC bus voltage. This device has been blocking this voltage. So this device is being turned on, therefore the voltage then starts actually falling, and I have shown this is linear. Many a times the voltage may fall rapidly and then the voltage may slow down and fall like this also. So let us say that this falls like this now. So you can see that the moment the voltage falls, there is certain voltage difference between the DC voltage and here, which is actually being blocked by the diode. So the diode is already reverse biased and it is blocking some amount of voltage. Therefore you can see that the diode has stopped conducting by the time, and the entire amount of current that the diode was carrying prior to the turn on transition has already been transferred to the IGBT. The IGBT current actually has risen almost to its full value by the time the voltage starts falling. So now on top of it, what you really have is it is a little on the higher side. So this is basically the reverse recovery current. It is just the load current plus the reverse recovery current of the diode flows through that, and after that it is a steady current here. So well before the voltage starts falling, the current has reached its peak value. I mean it's by the time, and well before that the current started rising, and the time that the current takes to rise is typically called the rise time, and the gating signal might have been given not just at this instant but a little ahead of this instant, and there is certain amount of delay time which is usually called as the turn on delay time. So which is not much of concern now for us, because our problem is essentially we are looking at the voltages and the currents. So this is how, let us say, this is illustration of a typical turn on transition. So the voltage is falling here, but before that the current has risen. So now if you consider the product of voltage and current, you can see that the product of voltage and current is 0 up to this point, but from this particular instant the product of voltage current increases. So it will go to high value, and then it will start falling. It will start falling, reach here now. So starting from this instant to this instant, there is going to be a significant amount of power loss, and that is what is the power loss due to this transition, and the peak power dissipation is going to be somewhere here, which is roughly equal to the DC voltage multiplied by the load current. So this is what I said, if this is 600 volts, this is 100 amperes, it is the product of that. Okay. Now let us say it is going to happen. So there is a certain amount of energy. So if you multiply V and I and you integrate that over this interval, which is the switching interval, that is going to give you the amount of energy that has been lost because of this turn on transition. So that is a certain amount of energy loss, which is called as the turn on energy loss. So similarly, let us say the device is turning off, it is conducting some current and that current falls when it is turning off. So it may fall rapidly, and sometimes it may fall rapid initially and then it will slow down. So it is kind of more gentle than this, which you can but so sometimes you can represent that as a double slope. So that is what I am saying is the current, instead of falling sharply down, it initially falls sharply down and then it slowly tapers down. So this part is represented like this, I mean asymptotically, like two straight lines for purpose of convenience, and this is sometimes called tail current, TAIL, tail, because it is like a tail. So this is that. So before the current starts falling, once again you see that the voltage has hit its limit, and there is certain amount of small amount of voltage spike also. See here I am just trying to illustrate, these are not exactly the switching characteristics as you would really see when you conduct an experiment to measure the switching characteristics. I mean you see that there could be a little different, but I am just trying to show how it will be. For example, this may not be a straight line, but this could be something different. It depends on the parasitics and many things like that, alright. But what you can normally see is you can see certain amount of over voltage spike, which is caused on account of this di by dt etc. When a time it turns on and turns off, there is a more voltage spike. And so that is the reason this, if let us say this is the DC bus voltage, you would choose your device voltage rating to be significantly higher than your DC bus rating. So for example, if you have a 1200 volt device, you will not use it for a DC bus voltage like 100 volt, I mean of 1000 volts or 1100 volts. You may use it only up to something like 800 volts, some 600 to 800 volts is the DC bus. So for 600 to 800 volts of DC bus, you will be using a 1200 volt one. This also assumes that you have done a very good bus bar design. You have to make sure that the stray inductances are all very low, otherwise the spikes can even be much higher. That is, it's when it is all turning at this instance, there is a lot of di by dt etc. So there are the parasitic inductances can actually cause very high amount of voltages there. Anyway, our present problem is not to really look at those parasitics and over voltage spike and so on and so forth, but our present problem is to understand the turn off transition and what is the device loss during that time. So if you say, if this is how the current falls and if this is how the voltage across the device is, then it is the product of these two. As you can see here, the product is almost 0, and again here also the product is almost 0. That is, this is before the turn on. So during this time it would have been conduction loss. This drop of this would have been the forward drop, which is actually very small. Again here there is the conduction is 0. So this is off state, there is no loss now. But over this interval from here to here, you find that there is some amount of good amount of power dissipation. So if you plot the product of V and I, you will see that it sharply rises and reaches a peak somewhere here, and then starts falling gradually and starts falling, and from here the fall might become more gradual, and finally it will come and reaches 0 here. So this is the instantaneous power dissipation. This is how it varies, the product of V and I. And if you calculate the area under that, you integrate this over the switching interval, you are going to get the energy lost during turn off transition. So this is what is called as E off, energy loss during turn off transition. So this E on and E off, turn on energy loss and turn off energy loss, are important for us to evaluate the overall switching loss. So the IGBT turn on energy loss, how much is that? Is it 10 millijoules, 50 millijoules, 75 millijoules, 125 millijoules? It actually depends on the DC voltage, obviously, because you can see that the power is the product of voltage and current. So it depends on the DC voltage, it depends on the current, and it also depends on the junction temperature. It depends on the device transition times. Here I am talking of a particular IGBT. So for a given IGBT, if you switch it at higher voltage, you would expect that EON to be higher. Similarly, if you switch it at higher current, you would expect the EON to be higher, and again junction temperature also has an influence on that. So or the operating temperature, maybe junction temperature and or case or something, whatever is related, and junction temperature is usually about 120 degrees Celsius is taken as the highest permissible junction temperature. Alright. So about the turn off energy loss, which is designated by this, which is we use the symbol E off. This is also a function of DC voltage. Of course, if you are switching off a device, it has to have certain amount of energy lost. If you are switching only 100 or 200 volts, the energy loss is going to be lower. If you are switching 500 or 600 volts, the energy loss is going to be much higher. Therefore, you can see that it depends on the DC voltage, or increases with DC voltage that was being blocked, and it also depends on the current that the device is going to conduct, or it was conducting, because the turn off loss, it was conducting some current. So it depends on how much current it is. If it is 20 amperes, the loss has to be much higher than if the current is 10 amperes. Alright, we could even say they are roughly proportional as far as current is concerned, and also it depends on the junction temperature. So there is also diode reverse recovery energy loss. You not only have the IGBTs, you also have the anti-parallel diode, and every time the diode is turning off, there is something called what is called as reverse recovery process in that. So there is a certain amount of energy loss associated with that. So this loss is also known. These all we need to get them from the IGBT data sheets. So if there is a particular IGBT data sheet, let us say there is a 75 ampere 1200 volt IGBT with anti-parallel diodes. So that would give you these this E on E off. It might give E on at some 2 or 3 different DC voltages. It will give over a range of current, something like 5% or 10% to the rated current. It will give you E on, and it will give again for 2 or 3 temperatures, either junction temperatures or case temperatures. So same way, the EF data will also be available from the IGBT data sheet, and the diode reverse recovery this may also be available from the data sheet now. And so these are certain references which tell you how these measurements can be made. For example, it is a little difficult to measure this current. Now, let us say you got to measure this current. This is how the current rises. It is very difficult to put in a current probe anywhere here. For example, you can't put a current probe here. This is all within a package and they are all tightly connected, meaning the parasitic inductances are very low. So, you really can't put a current probe anywhere here or so. So, you need some special arrangements to do that, and one such special arrangement is actually what is called as a coaxial current transformer. So, what is done is that you have a module, there is a particular device and there is a particular terminal of the device, and this coaxial current transformer, it has got a primary winding which has got a coaxial structure, and so like current will enter, let us say, through the inner limb of that coaxial primary and will go out through the outer limb, so into the bus bar plate or whatever. So, the primary will have a coaxial structure and the secondary, there is an annular region between the middle of the primary. So, the secondary will be seated inside that, and therefore, that will have a very low amount of leakage inductance. So, this coaxial current transformer has a particular kind of structure and has low leakage inductance, and therefore, it is possible for you to use these and make measurements. What will happen if the inductance is high? If the inductance is high, then as I just mentioned a while back and I have mentioned in some previous lectures, the devices will fail because the parasitic inductance increases, there is high di by dt. So, L di by dt is going to be causing some over voltage spikes and the devices are going to have over voltage failure. So, you cannot introduce current measurement system which will actually increase the inductance. You have to do it in such a fashion that the inductance is not increased significantly, and coaxial current transformer is one way of doing that. So, this will not give you much great amount of increase in the current, you can still go about doing it now. So, these are some papers which actually talk about this coaxial current transformer. This is one paper on how you can go about measuring the switching characteristics. I had given you some switching characteristics more indicatively. It is possible for you to measure these characteristic curves. This is how the data sheet values have actually been given or whatever, and sometimes the data sheet may not give you the correct value, exact value that you want. You might want data for 800 volts DC bus, but what may be available is only for 600 volts and 1000 volts. So, there are times when you might want to measure, and so the data may be available for some case temperature, you may be operating at some other case temperature. So, many times even though you have data sheets, you might want to make these measurements, and as newer and newer devices come, you actually have to do this kind of characterization. So, this is actually a paper which talks of how do you do this characterization, how would you measure the switching characteristics of semiconductor devices and using a coaxial current transformer. So, this is the second one is a much later work of measurement of IGBT switching characteristics and loss using coaxial current transformer. So, this reports certain things on how exactly you can build one and design and fabricate one, and how you make certain amount of measurements. So, these are all about measuring this E on and E off. The third one is also something similar, whereas in the first two cases they use the coaxial current transformer. Here it is a Rogowski coil is used, and these are actually high power traction converters. So, in the traction converters, how would you measure the switching characteristics of IGBTs? So, that is what it is about. So, these are some references which can help you understand this E on and E off, like how you can measure this turn on energy loss and turn off energy loss, and how these turn on energy loss and turn off energy loss vary with the operating conditions and the environmental conditions. By operating conditions, I mean like things like the DC bus voltage and the current that is being switched, and the environmental condition, I mean the let us say the ambient temperature. Alright. So, those are some references which could give you better insight into that. Now, let us say those E on and E off are available. Now, how do you go about calculating the inverter switching loss? So, one assumption we normally do is the DC bus voltage is constant, that is you have an inverter and the inverter is being switched, it has some DC voltage and is being switched, and it is applying some AC voltage on a load, or let us say a motor, something like an induction motor. So, actually the DC bus voltage will be varying over a line cycle, there will be some ripple on that, there could be some 300 hertz ripple, 150 hertz ripple, whatever. But what we are one simplifying assumption we make which is reasonable is that the DC bus voltage is constant, whatever variation is there in the DC bus voltage we are ignoring that. Then you have this E on and E off which are available in the data sheets, and sometimes they could have been measured, as I was just talking to you a while back. So, these E on and E off vary with the load current, you can say roughly proportional to the load current. So, they vary with the load current now. So, now what is this load current? The load current has a fundamental component and also has got a harmonic components. Now, at fairly high switching frequencies, you would say that the harmonics are fairly negligible compared to the fundamental current. So, this is an assumption which we have made earlier also while calculating conduction loss, while calculating DC link ripple current, DC link current we did this. So, the same kind way we can say that the harmonics or the ripple in the load current can be neglected. So, you can consider only the fundamental component of the load current now. So, what you need to now do is you have to look at the variation of the switching energy loss, that is variation of E on and variation of E off. So, with current. So, if current varies in a sinusoidal fashion, E on and E off would also vary probably in a roughly in a sinusoidal fashion. So, now this variation you can E on can be expressed as E on as a function of I, similarly E off as a function of I. So, this data will be available for you from the data sheet. So, you might be able to approximate that relationship by a simple function, say sometimes a linear function, sometimes a piecewise linear function, or let us say a parabolic function. So, some such approximations might be possible for you. So, once you know this, you know the relationship between the energy loss and the current, and you have also simplified it in some sense so that the calculations can be easier. Once you have got that, you have to calculate this average switching energy loss over a half cycle or full cycle of the line current. So, here it is easier, for example, if it is a nice function for you. For example, if the average switching loss varies like a rectified sinusoid, it is much easier for you to do the calculation. So, that is why you make use of some simplifying functions here. So, now the switching energy loss, since you have expressed it as a function of current and the current is again a function of time or fundamental angle, you can integrate the switching energy loss over one half cycle of the current and you can consider its average value. That average value will give you the average switching energy loss. So, what do you mean by that? See, there is an inverter leg. Now, that inverter leg, let us say it is switching a current, the load current is about 100 ampere peak. If that inverter leg is switching 100 ampere current, then the switching energy loss is supposed to be high. The same time, if it is switching only 50 amperes, the switching energy loss is expected to be lower, maybe roughly half. If it is switching only something like 1 ampere or 2 ampere, the switching energy loss is much lower than that. Therefore, the switching energy loss varies with current. The current varies in a sinusoidal fashion. The switching energy loss might also vary in a sinusoidal fashion. It is arguable whether it would vary in a sinusoidal fashion or not is a question. Well, sometimes you can approximate and say that it could be in a sinusoidal fashion, but it certainly varies with the current and therefore with the fundamental angle. So, there is something called average switching energy loss that you would actually calculate. So, this average switching energy loss means like for one turn on and turn off, this is the amount of average loss, energy that is lost. If you multiply that by the switching frequency of the inverter, you would be able to calculate the switching loss. So, this is roughly the procedure for calculation of inverter switching loss. It is fairly simple. So, you basically need this E on and E off and you have the simplifying assumptions, and E on and E off as functions of current and you ignore the harmonics, etc. You can go about doing it now. So, there is some little catch now whether it is a continuous PWM or discontinuous PWM, as that is what something we will come down to now, but this is roughly the procedure. Alright. So, what will happen if it is a discontinuous PWM? There will be bus clamping, and during bus clamping the energy loss will be 0. It will not, the energy will not, there will be no switching energy loss because there is no switching whenever a particular leg is clamped. Let us come to that little later. So, let us first look at sinusoidal PWM. So, 3 sinusoidal signals R, Y and B. Y phase is being represented by a green signal instead, just for it's easier to see. So, therefore, I have given it as 3 same modulating signals, and you would of course compare it with the high frequency triangular carrier and produce the PWM signals. So, the comparison of R phase with the carrier and Y phase with the carrier and B phase with the carrier would give PWM signals which would switch the R, Y and B phase legs, as we know very well. And so, the inverter is running. So, there is some current flowing through that. Now, let us say this is the amount of fundamental current flowing through that. So, this is the R phase modulating signal. So, the R phase voltage, fundamental voltage is proportional to this. Here I have shown it as something like a modulation index of 0.8. So, there is something like 0.8 into VDC by 2 would be the peak phase fundamental voltage. Let us say VDC is 600 volts. So, VDC by 2 is 300 volts, 0.8 into 300 is 240 volts. So, the inverter is applying a peak phase fundamental voltage, a fundamental voltage whose peak value will be 240 volts in this case. Let us say that is being fed to a 3 phase load and it is a linear load. So, it draws some kind of sinusoidal current. So, the non-sinusoidal part, then this is only the fundamental component of the voltage. There is also the this represents the fundamental component of the voltage. There are also harmonics. Those harmonic voltages would cause harmonic currents, but we assume that the load filters it out very effectively. They are at high frequency, harmonic voltages are high frequencies, and it is effectively. So, therefore, it is effectively it is only the fundamental current that is being considered here. So, let us say this is fundamental current. Well, as I said, actually there could be a small ripple, but you can ignore now. So, when you have this current, so now the next question is what happens? There is energy loss. So, every little switching cycle, now on this fundamental cycle of 360 degree, you will have several switching cycles. So, something like every degree, every 2 degrees or something like that. For small things you may have a switching, I mean you have one cycle of switching. So, is there energy lost in the device on account of switching? Yes. How much is the energy that is lost on account of switching? Okay, let us say we will take choose some other color than red, because this is already red. Would green be alright? Yes, let me take green. Now, if you look at here, the current is 0, and therefore, the amount of energy that might be lost is 0. It may not be 0, it may be a very small thing. So, let us say this is the energy lost somewhere here, and for every value of current it is possible for you to find out how much is the energy lost, and the energy lost might rise like this. So, this might be the relationship. Let us say for this value of current the energy lost is like this here, and for the operating conditions it may be like that. So, the energy lost might actually go like this, it might actually vary like this, and might come to something of this nature. So, what is it that I have plotted? I have plotted the switching energy loss. You can say that this is E on plus E off. You can say this is E on plus E off. I am sorry, it is a little unclear. Let me check if I can. All right. So, during a turn on it is going to have certain loss, which is called as E on, and during the turn off it is going to have certain loss, which you would call as E off. So, this sum of E on plus E off is like in one switching cycle. So, but that let us say varies like this. Now, what will happen again here? It will be the same thing. The current may be reversed, but the current reverse means what? Here one transistor and the other diode are conducting. Here the other pair of transistor and diode will, if top transistor and bottom diode conduct here, the bottom transistor and the top diode will conduct here. So, it does not matter. So, how would the E on EF vary? This will again vary something like this. This would again vary something like that. So, this is how the nature of variation of E on and EF is going to be. So, how is this variation? You can say it could be roughly sinusoidal if you ignore certain things, if you say that this is proportional to the current now. So, you have certain average value, you can evaluate certain average value, and this is the average value. You would take it as the average switching energy loss and multiply it with the switching frequency to calculate your switching loss, the power that is lost here now. So, what we are going to now look at is the same sine triangle PWM, but I am looking at a different power factor. So, if you see the power factor is something like 45 degrees lagging here, and here the power factor is almost 90 degrees. When the phase is at its voltage is at its peak, the current is at its 0 now. So, what happens to my loss? You see there is certain amount of loss. What decides the energy loss? It is the DC bus voltage. It is not the fundamental phase voltage, it is the DC bus voltage, and the DC bus voltage is always the same throughout. So, once again what you will have here is you will have the same kind of energy loss, you will have a similar kind of energy loss, there is just a phase shift here. You will have, this would be your nature of energy loss. So, if you look at the difference between here and the previous one, so you look at this and that, there is no difference, there is a difference in phase, otherwise there is no difference. So, there is the variation of the switching energy loss is quite similar, and its average value will be equal. So, what does it mean? What is the difference between here and there? Is the load current is same, but the power factor is different. So, even if the power factor changes, you can say that the switching loss does not change significantly. If we are looking at sinusoidal PWM, first we are looking at sine triangle PWM. So, there is load. Now, the average value depends on what? It certainly depends on this peak value. What does this peak energy loss depend on? It depends on the peak current. So, if the peak current goes up, then this will also go up, its average value will go up. So, the switching energy loss certainly depends on the peak value of load current. That is very clear, and it is quite, it is just common sense. So, it is like that, but it does not depend on the modulation index. That is a very interesting aspect. Well, it might indirectly depend in the sense that this modulation index determines the output voltage and that determines the current. So, but it is a function of current, it is a function of the DC bus voltage, and it is not a function of power factor. So, you can see that for different power factors the average value is unchanged now. This is for sine triangle PWM, and this is actually true for any continuous PWM. You can add third harmonic injection, that is any continuous PWM where your signal is actually, a modulating signal is a continuous function of time. An example would be third harmonic injection. So, here also what would matter is, I have not shown the current here. Let us say the current is same as what you have here. So, that would mean the current would actually have a zero crossing, we will go like this, well, zero crossing at the peak of the fundamental voltage, and it will go like this, and at this here it will have its peak now. If you have the same current and this is same, so here also it is 0.8, the fundamental voltage is 0.8, here also the fundamental, I mean the modulation index is 0.8, but here you have just added a common mode component, so it does not matter. So, the fundamental voltage applied is still the same. So, the same load, it might carry the same current. So, let us say that it was 0.6 per unit was the current, as we saw last time, it is the same current, and so the loss will be the same, the switching loss will be the same as what you get here. So, the switching loss does not change when you go from, let us say, sine triangle PWM to third harmonic injection, whereas conduction loss changes. Conduction loss changes because it depends upon the duty ratio of the switches, and the duty ratio depends upon the actual modulating signal. Whereas switching loss, it largely depends upon the current, it depends on the DC bus voltage and the current. So, its amplitude and the power factor of the current. Again, interestingly, for continuous PWM methods, it does not depend on the power factor also, it largely depends on the current. So, it is DC bus voltage and the current are the main parameters here. Alright. So, now instead of that, there is this conventional space vector PWM. You are not adding a third harmonic, but you are adding this 50% of the middle value of the sinusoid here. So, you are adding a common mode like this, which looks like a triangular carrier, and if you add that, your R phase modulating signal looks like this. So, when you do this and do your triangle comparison and do your PWM generation, what happens? Your 0 vector time gets equally divided, that is what we have seen before. So, here also what happens? Let us say the same 0.8. So, the fundamental voltage is same. So, if the same amount of current is applied as before, I mean the load current is same as before, you will say that the switching loss is same. So, whether it is sine triangle PWM or third harmonic injection PWM or conventional space vector PWM, the switching loss is not different at a particular operating condition, right, and it also does not change with modulation index. So, this is again third harmonic injection with where the harmonic amplitude is, third harmonic amplitude is 1/6 of fundamental, here the harmonic amplitude is 1/4 of the fundamental, fine. So, let us say that modulating signals, now from continuous let us go into discontinuous PWM. In case of continuous, the modulating signal is a continuous function of time, otherwise it could be discontinuous function of time. As we have seen before, switching loss does not vary significantly between one continuous PWM and another continuous PWM scheme. Example, sine triangle PWM and third harmonic injection PWM. This is what we just saw a while back. However, if we are considering discontinuous PWM, for example 60° clamp PWM and 30° clamp PDM, the switching loss would vary significantly between these methods. So, under the same operating condition, 60° clamp would give you some switching loss, 30° clamp would give some other switching loss. Why so? See, because bus clamping PWM, what they do is they clamp every phase to one of the DC buses over certain intervals. Which interval, which phase, that changes from PWM method to PWM method. For example, 60° clamp would clamp every phase in the middle 60° duration of its voltage, line cycle, half cycle of its voltage. 30° clamp would clamp every phase during the middle 30° duration in every quarter cycle. So, where it clamps changes now, and the modulating signal is a discontinuous function of time, which we have already seen. Several such modulating signals are possible. So, and these modulating signals result in clamping, clamping over different durations. No switching energy is lost when a phase is clamped, obviously, because if it does not switch, where is the energy, switching energy loss? Nothing. And So, there is certain amount of energy saved. Now, so there is conduction loss, but there is no switching loss when it is clamped. So, how much energy is saved on account of this by not switching? Energy saving is highest if the phase gets clamped around its current peak. If there is a particular phase, if the PWM ensures that the phase gets clamped when the phase is carrying its peak current, the current through a phase varies sinusoidally. Whenever the current goes through its peak, the fundamental current, if the phase gets clamped, then energy saving is highest. The energy saving is insignificant if the phase gets clamped around its current 0. So, phase current goes through 0. When it is crossing 0, if you clamp a particular phase, the energy that you are going to save is insignificant. So, switching loss you can see strongly depends on the load power factor for the PWM methods. For the same let us say 60 degree clamp PWM method, if the power factor changes, so this is going to change, whether you are going to clamp a phase closer to its current peak or clamp it closer to the current 0 is going to change, and therefore it changes. And you can now readily see that the switching loss depends on the load power factor for BC PWM methods, unlike the CSV PWM methods. So, the different PWM methods, the bus clamping PWM method, they are on account of these common mode signals. There are only 2 common mode signals that you can actually consider for clamping a phase, one of the phases. So, this would clamp one of the phases to the positive bus, this would clamp one of the phases to the negative bus. So, you call them positive clamping and negative clamping common mode signals. So, what you would normally do, as we have seen, is follow this for some 60 degrees, another 60 degrees, so 60 and 60. So, which 60 is the only question. You can follow this from 0 to 60, 60 to 120, 120 to 180, or you can follow this 30 to 90, here 90 to 150, and so on and so forth. That leads to different kinds of bus clamping PWM methods. This is something which we have seen before. Must have a periodicity of 120 degrees, it must contain only triplet frequency components, it must have 0 average value. If you ensure all these things, you will be making sure that the positive and negative clamping mode signals alternatively, I mean the whole operation is symmetric, and all the 6 devices will have equal amount of losses. We discuss this when we are discussing the PWM now. So, let us take the specific example of 60 degree clamping PWM method, because it is actually it clamps for 60 degrees and it clamps for 60 degrees around the positive peak of the fundamental voltage. Again, here it is the it's the negative peak of the fundamental voltage, here also it clamps for middle 60 degree. So, that is why it is called 60 degree clamp. It is just a nomenclature. In some papers you would find this as DPWM1, DPWM2, DPWM3, etc. are all names used now. Here it is also for the same modulation index of 0.8. So, the sinusoidal signal is same as the sine triangle PWM, etc. we saw before, but then you are adding this kind of a common mode signal, and therefore, your resultant modulating signal becomes like this. Okay. So, now how about the switching loss? Obviously, there cannot be any switching loss in this particular R phase, because here R phase is clamped. So, here there cannot be any switching loss in Y phase because it is clamped. Here there cannot be any switching loss in B phase because it is clamped. Okay. Now, what happens? How much energy is saved? That depends on what the load power factor is and where exactly it is clamped. Now, we are taking a situation where you can see that the load current, this is the load current, this is 0 when the fundamental voltage is maximum. So, you are looking at 0 power factor. So, the current is actually going through 0 and you are clamping a particular phase. So, what is the point? The energy that is lost on account of switching is very low here anyway, because the current is very low, and therefore, by clamping R phase here, there is going to be no significant amount of energy saved. So, the switching loss with this kind of PWM is going to be still quite high. Now, instead of, let us say the current is like this. So, let us also plot how that is going to look like. So, now the energy loss here will be 0, the energy lost here will be 0. How would the energy lost here be? That energy loss will be something like this. Will go like that. This is for R phase. So, once again the energy lost here will be 0. So, you will have the energy lost varying like this. This is how the energy loss would be, and then the average value of this is now. So, the average value, there is some reduction in the average value, but that is not too high because you have clamped only close to that now. On the other hand, let us say you go to something else, some other power factor. It is a lagging power factor, it is actually 15 degrees, but it is not too very lagging, it is certainly not 90 degrees. So, now what happens? You are once again you are clamping. So, when you are clamping, this is 0. Your whole thing would have actually been, your whole the loss would have actually been like this, but now what happens to that? During this region your loss is reduced, let me draw this with a different color, maybe not here, not this one. So, let us say here. So, what should have been so much is now reduced here, is now reduced. So, you get certain amount of savings in the energy, switching energy. During this time you do not save. So, the switching loss for the same amplitude of current, it is a different power factor, the switching loss is now lower. Now, look at this unity power factor case. Now, the loss is 0 here, and you would actually have your switching loss going like this. You might actually have it going like this. So, where the switching loss would have actually peaked, the switching loss would have actually peaked here, that you have avoided. So, you have saved a lot of switching energy in this region, and therefore, you have managed to reduce the switching loss. So, if for unity power factor, the same amount of load current, but the power factor is now unity, you will see that the switching loss is low. The switching loss will be lowest for 60 degree clamp PWM when you are looking at unity power factor. So, as the power factor goes on reducing, or the power factor angle goes on increasing, the switching loss will also go on increasing. So, you can use the same E on and E off, and here the energy loss is 0 because there is no switching, and you can calculate the average E on and E off, and you can multiply that by the number of switching cycles that it has effectively had, and you can find out how exactly the exact switching loss can actually be calculated, because the energy loss is known to you. This is how energy loss is, and then you also know the switching frequency, how it is going to change here, except that you have got to account for this particular factor. Alright, so this is again the procedure. This is just a small modification in the way you calculate when you do a discontinuous PWM. The same thing can be done for all these methods. So, during this region, the switching energy lost in R phase IGBTs is low. So, you can avoid that, you can actually do this calculation for continual clamp PWM. So, this is yet another continual clamp PWM. So, here also the procedure is very similar. So, here you will see that this is good, the switching loss will be lower if the power factor is leading. So, if the power factor is leading, let us say by 30 degrees, this will give the best switching loss, will give you the lowest switching loss. So, at other power factor, so power factor angles between 0 to 30 degree lag, it is reasonably alright. Lagging power factor angles, this is not a very good idea, whereas this is a very good idea for lagging power factor angles. For lagging power factor angle of 30 degrees, this gives the lowest switching loss for a given current amplitude. So, typically for an induction motor drive, it might be a good idea to operate with such a continual clamp PWM method, because induction motor drives, they operate at lower, some lagging power factor angle. So, it could be 30 degrees at full load, something like 0.866, you are going to be very close to this. So, this is one generally for lagging power factor loads, this is a good thing to use now, whereas this could be a good thing for leading power factor loads, and this kind of 60 degree clamp could be a good PWM method for unity power factor loads from the point of view of switching loss. Alright. So, these all it depends on, depending actually on the power factor, you can actually vary your PWM location now. So, if it is leading, you can make sure that you can up to some point, as long as the load is lagging or leading and the angle is not more than 30 degree, it is possible for you to clamp the phase exactly when its current is around its 0 crossing, for 60 degree duration around its 0 crossing. So, for example, here if your current is having its peak here, you can clamp it, so you can clamp it around 30 degrees before and 30 degrees after the current peak. Okay. So, this is actually good when you actually go to 0 degree power factor. So, what you can do is you will not be able to clamp a phase when it is carrying the highest current at 0 power factor. Why? Because when the current is at its peak, the voltage will be at its 0, and when the voltage is at its 0, you cannot clamp a phase, because only a phase having this higher modulation, maximum modulation index or minimum modulation index can be clamped. That M mid, if you call this M max, M mid and M min can be clamped, or the phase corresponding to M max can be clamped, but M mid can never be clamped. So, you can never clamp a phase carrying the highest current at 0 power factor. So, but this is actually a good idea for 0 power factor. What will happen here is you will find that the highest current carrying phase will not get clamped, but the second highest current carrying phase will get clamped, and which is the best thing that you can do in this case. So, for 30 degree clamp PWM also you can actually evaluate, like you have your E on EF available from the data sheet, and the switching energy loss is 0 here, otherwise it is there, and you know the number of switching cycles that it undergoes is known for you, therefore, you can arrive at your energy loss. Alright. So, this is another variant of split clamp PWM. This will be good for some power factor angle between 60 and 90 degrees. Alright. So, this is again for leading power factors between 60 and 90, it might be good. Alright. So, the same thing you can actually look at it from the space vector point of view, it is a revolving vector. Now, what happens, as we saw, we are going to apply vector 1, vector 2 and 0 for different times, and we are going to realize the vector. The difference comes in switching sequences. So, this is how we calculate all the times, as we have discussed several times before. Now, we are going to apply these different states. Excuse me. Here what happens, R phase switches, Y phase switches, B phase switches 1. So, all this there is certain amount of energy loss, let us call this as ER, energy switching energy lost on account of R phase, this is EY plus EB, the total energy lost is ER plus EY plus EB, and ER is a function of the R phase current IR, EY is a function of Y phase current IY, EB is a function of the B phase current IB. Now, if you go here, the B phase is not switching. So, here what you have is only ER plus EY, and again ER is a function of IR, EY is a function of IY, and EB there is no loss at all. So, you save certain amount of energy here, if this is when you are looking at as in a sub cycle by sub cycle basis. So, it is only ER plus EY, where ER is the energy loss, switching energy lost in R phase, and EY is the switching energy lost in B phase, Y phase. So, ER plus EY. Same way, R phase is clamped here, the energy lost is only EY plus EB, and EY is a function of IY and EB is a function of IB. So, if you are considering the same value of TS, these things will give you, these bus clamping PWM schemes will give you lower value of switching loss than conventional space vector PWM. That is only if you consider the same value of TS. Normally what you may do is you must reduce this TS to 2/3 of whatever its value for conventional. For conventional PWM, if you have 100 microsecond, you can have TS is equal to 67 microsecond for bus clamping PWM. So, that both of them would switch at the same average switching frequency. You do this to improve your harmonic performance. So, in that case you really need to work out and see whether there is an improvement or not. So, if you maintain the same TS, then bus clamping PWM schemes are capable of reducing your loss by something like 30% to 50% switching loss compared to the conventional space vector PWM. Here you have a different case, there is R phase switches, but Y phase switches twice, B phase is clamped. So, what is the energy lost? The switching energy lost is ER plus 2 EY, because this is the Y phase current is not going to be significantly different between this instant and that instant. There is R phase current, this ER is a function of IR, EY is a function of IY. So, it is ER plus 2 EY is the energy lost in the sub cycle, EB is equal to 0. Is it a good, is it not, does it have any advantage or disadvantage? It depends on whether EY is higher or EB is higher. In case EB is higher, you are avoiding that switching and you are switching EY once. If EB is greater than EY, this is advantageous. If EY is greater than EB, then this is disadvantageous, as simple as that. The same logic can be applied here for 7212. So, here what happens, R is clamped, but Y phase switches twice. If ER, that is the switching energy loss of R phase, is greater than the switching energy loss of Y phase. For example, R phase is close to its peak current, R phase current, whereas Y phase current is close to its current 0, then this is advantageous. If Y phase current is greater than R phase current, this may be a disadvantage. Now, this is the same thing where I have shown the sequences like this. If it is conventional, you go around and you come back. This is the conventional space vector PWM, any continuous PWM. So, in continuous, the only difference is, conventional space vector you stay here for 0.5 TZ, T1, T2 and 0.5 TZ. In the other methods, it may not be 0.5 TZ, it could be 0.2 TZ, T1, T2 and 0.8 TZ, but does not matter, same number of switchings and the same amount of switching energy lost. So, in the bus clamping, excuse me, you are avoiding this B phase switching, which is what I mentioned before now. So, this you can now look at whether it is advantageous or disadvantageous. If by clamping B phase, if B phase is carrying a high amount of current, this could be actually an advantage. Now, this is now here I have shown 721 127. This is, you are switching like this is another bus clamping PWM sequence. If R phase carrying is a high current this would be advantageous. Now, the 0 1 to 1 once again would be an advantage if B phase carries higher current than Y phase, because Y phase there is going to be a double switching. Similarly, you have 7212 and 2127. So, here again you have this situation where you will see that this is when R phase is not switched. So, when R phase carries a high current or the switching energy loss corresponding to R phase is high, it is better not to switch R phase, and if for example Y phase has got a lower current, this might really be an advantage to do that. That is one way of looking at it. Then the same way you can look at the other sequences like 1012 and 2101. So, what happens? You start from 1, you stay here for t1 by 2 seconds, you go here and stay here for tz, you come back and stay for t1 by 2 seconds and go here and stay for t2 seconds. So, you switch R phase twice. From the switching loss point of view, this is a good idea only when R phase carries low amount of current and particularly R phase should carry a current which is significantly lower than the current carried by B phase. So, you are going to avoid B phase, you are going to use R phase, double switch R phase. So, similarly what you are going to look at is here if you use for example 2721, you are switching B phase twice. This is a advantageous in a situation where R phase has no energy loss, whereas B phase R phase has high amount of energy loss and B phase has got a lower amount of energy loss. So, these various sequences are there for the same amount of Vref and depending upon the current, and that is essentially like the relative values of the currents of the 3 phases, they prove to be either an advantage or they prove to be a disadvantage. So, you can always calculate. So, once you have the energy losses available, you can also always you can calculate the switching loss for various PWM methods also. So, what we will do, we will look at in the next class, we will look at some design of PWM methods for low frequency for reducing the switching loss. So, here are some references which tell you how you can calculate the conduction and switching loss for some continuous and discontinuous PWM method. And here in this thesis, part of the thesis is about calculation of switching and conduction losses. So, this would actually give you some example of continuous PWM, discontinuous PWM and an advanced bus clamping PWM also. And this is one other paper where the effect of all the losses about the rise in junction temperatures etc. So, such things are actually discussed here. And these are some references where you actually have the advanced bus clamping PWM methods. So, some of these contain switching PWM methods which have an advantage of reducing the switching loss over the conventional methods at under certain operating conditions. So, we will be discussing certain ideas from these methods in the next lecture, which would be essentially on designing hybrid PWM or PWM methods for reduced switching loss. So, I thank you for your interest in this lecture series. I thank you, I hope that this lecture was useful, and look forward to your continued interest in the remaining lectures. Thank you very much.